Thank you. Well, we will do the presentations one after the other, and then we will take questions together. So I'm going to present you something I have already presented before, but just to go on with the same thing, that is in vitro correlates of heterologous protection using avidity and subtyping ELISAs. We know that FMD vaccines are based on inactivated virus, and there is no cross-protection between and in some cases even within serotypes. So we usually do challenge tests to see if we have protection. But of course, we prefer to use a serological approach, but that serology data has to be correlated with protection to be able to use it. And right now, the current assays are just the virus neutralization test and the liquid phase blocking ELISA. So basically what we do when we want to study cross-protection, we want to know if a vaccine is likely to protect against a particular field strain. Then we use that vaccine, we vaccinate the animals, we do serology and challenge at the same time. And then if we are lucky and we can correlate both, then we can have a prediction of protection. So right now, what is being used is a ratio between the titer against the field virus and the vaccine virus, and there is a cutoff for that. And the thing is that sometimes using these assays, we cannot answer this question if a vaccine is likely to protect against specific field virus. So there we are. So the thing is that sometimes the R values are not consistent, and this graph is quite good in showing virus neutralization titers in the x-axis against the vaccine strain, and in the y-axis against the field strain. And then you got the dark dots are protected animals, and the open circles are non-protected animals. And between brackets, you have the R values. And the thing is that, for example, all these that has been highlighted there, they are animals that were protected, and if you go to the R value, the R values are predicting they will not be. And it happens the other ways. So when you go to individual animals, the R values are not very consistent. The thing is that, in fact, we are measuring only the amount of antibodies and the neutralizing activity, and there are other mechanisms of protection mediated by antibodies that we are not looking at. So in fact, there are many others, like those that are hidden for us, that we are not evaluating. And most of them, they have to do with the Fc receptor, so it has to do with antibody-dependent mechanisms, apart from just neutralizing the virus entry to the cell. So that prompted us to think that, in fact, the amount of the neutralizing antibodies or the amount of antibodies or the neutralizing activity are not the only correlates, possible correlates of protection when we are thinking in a virus infection. So we decided to measure other aspects of the protective antibody response. And along the years, we selected something that is very easy to measure. And those are the isotype of the antibodies, which is related to the function in mediating protection, and also the avidity of those antibodies. And the avidity is a functional affinity. So it's the way the antibodies in a serum sample binds to the antigen, how strong they bind. And the avidity is influenced by many parameters, but it's a hallmark also of a good immune response. So it has to be with individual affinities, of course, the amount of antibodies, and also the diversity, and even the isotype, although that is in the Fc of the antibody, in some way is related also to the way it binds to the antigen. So what's the information provided by serology? In fact, we measure with liquid phase blocking ELISA how many antibodies were induced. We measure with a VNT how the antibodies prevents virus entry to the cell. And now we added like two other parameters, two other aspects, that is to measure the isotype profile. So we have the IgG1 and 2 ELISAs, and the functional affinity with the avidity ELISA. And in fact, we developed tests, very easy tests, to measure these other aspects of the antibody response. So, and it's not just because of the immunology, but the thing is that VNT is labor intensive. I'm pretty sure everyone has dealt with VNTs. And it's very difficult if you want to do high throughput assessments. It's very hard to work. You need facilities like virus, cell culture. Liquid phase blocking ELISA is easier, but you also need to set up the detecting antibodies and the capture antibodies, and then that takes time, it's difficult to standardize, and if you have a field sample, it's kind of a nightmare. So we decided to move to easier assays, and this is the IgG1 and 2 ELISAs that were born more than 20 years ago, I think. So they use purified virus stick on the plate, and then you put the serum sample, and then you come just with an anti-IgG1 or 2 conjugate. That's it. And then you get a titer, you make dilutions. Very simple ELISA. And for the avidity ELISA, you have to run the samples in duplicates. Always, well, the purified antigen is stick on the plate. Then you have duplicate wells with the serum samples. And then you do the PBS wash. Here is animation. Yeah. So all the antibodies that are not bound to the antigens are removed. The same for the avidity ELISA. But you also apply urea, that is a chaotropic agent, that will detach all those weak binders. Look, they are gone. So then when you come with a conjugate, you get like a different color, and you can get a rate of those values, and then the readout is the avidity index. So it's quite a simple assay. So we published 2 papers quite long ago. I'm going to go through them quite quickly. But the thing is that we used an heterologous challenge study that was performed in Argentina in 2006, and we used 64 samples of animals that were vaccinated with A24 Cruzeiro, that's a vaccine strain, and they were challenged with a field virus, the A Argentina 2001. And so, after challenge, we saw that 47 animals had symptoms and 17 were protected. So using these samples, we tested all our assays, and I don't want you to pay attention a lot to all the numbers, but here what we summarize in this table are the values of sensitivity and specificity of all the assays, even against the homologous virus. So we tested it against the heterologous and the homologous virus. And what comes out from this, here we have the R1 values, the VNTs, IgG1, IgG2, avidity, and also the ratio between the titers. And so what we see here is that the specificity of all these assays is very good, but the sensitivity is unacceptable. It can go down up to 0.12, and that's the R1. So it's really bad, except for the IgG1-2 ratio that gives quite an acceptable sensitivity, 70%, but it's not good. So the problem that we have when we are predicting cross-protection with serological assays is that we have low sensitivity. So a way we tried to figure out how to solve this issue was to use the conditional testing. So not just one assay, but combining 2 assays. So we did a first assay, and then samples that are not detected as protected, they are run by a second assay. So we trust in both assays to classify the animals as protected. And doing that exercise, in fact, and this I show you only the best combinations, we see that the sensitivity increased to acceptable levels. You see there almost 0.9. And the nice thing is that we can combine just the avidity and the isotype ELISAs, and then you can have an accurate prediction of protection. And this is really easy. It's just few ELISAs and you have a result. So we can combine these assays to improve the accuracy of serology in predicting protection. It can be these assays, it can be other assays, you can use VNT as well, but the concept is perhaps we need to see more than one aspect of the antibody response to get an idea of how cross-protection can work. And this is an example of how we applied the assays to another heterologous study. This is just an experimental study, a small study where 5 animals were used per group. And the animals were vaccinated with these vaccines that you see there. All of them, they contain A24 Cruzeiro in different doses. One group has 2 doses. And as you can see, and this is the only thing I would like to highlight, not to go through the whole assay, But you can see there that we have 3 non-protected animals. And if you want to see which assay correlates better with protection, and then here we have the neutralizing antibodies on top and the total antibodies measured by liquid phase blocking ELISA below. And you can see that there's no relationship between antibody titers in this case and protection. And if we order the animals based on their titers, you will see that the red ones that are the infected animals, they are almost anywhere. So it's not related to a lower amount of antibodies or a lower amount of neutralizing antibodies. But the thing is that when you measure avidity, then we can really discriminate between protected and non-protected animals. Although this is a small sample, it's very clear. And you see there that non-protected animals have low avidity antibodies against this field virus. But these animals, they did not only have low avidity antibodies against the field virus, but in fact, they have low avidity antibodies against the homologous virus, so the virus in the vaccine, and also to a non-related virus of another serotype. So these animals have low avidity antibodies against FMDB. And we should be able to predict it even when using the homologous strain. But of course, this is preliminary data, and we have the tools now, but they need to be validated because we have been using them just with our samples, with our strains. So we need more people to be able to use these assays for us to know if they really work. So the technology transfer has already started. So I've been to several places all over the world. I really enjoy going everywhere. And so we have deployed the assays to South Africa, to Australia. We have started, of course, in our country. And this year I was in the Perbrite Institute with Anna and her team. So I think that it's very important to have the assays so that they can be tested like in different settings, with different samples, with different strains, and start finding out if they really work. And well, I would like to acknowledge my collaborators in Argentina. So that's the list of the guys in blue are from Argentina. Also Biogenesis Vago, that's the company that formulated the vaccines that we use in all these studies. And of course, NASA. And right now, we are working together with Richard, David, and Anna. We have, look, what a nice picture that one. We are the FAO HQ expert group in FMD vaccine matching. And with this one, I would like to give the word to Richard. This is my group in Argentina. So thank you very much, and we take questions afterwards.
Alejandra's pretty much said everything already, so I can skip through most of my slides. But we were funded this year by EuFMD with their FAR fund to try to bring this together and properly validate these assays in different labs using more animal antisera. I just thought I'd start by saying why this is such a problem. I mean, Alejandra's already touched on it, but this is from the OIE manual about how we choose our values at the moment. You can do it using the liquid phase or using VNT, and there are values that we're supposed to choose that will do this. And in particular here, the VNT advice from the manual says values less than 0.3 suggest that the field isolate is so different from the vaccine strain that the vaccine is unlikely to protect. And of course, this was blown out of the water 10 years ago now by this lovely study from FLI, which essentially just showed that relationship didn't hold at all. And that's obviously slightly embarrassing when it's still our principal method for doing vaccine matching. And the problem here is that these vaccines are all so good that it's completely irrelevant that the antigenic match is so poor because the quality of the vaccine has just overcome it. At least that's the working hypothesis for what's going on here. Yeah. So what this comes down to is the fact that there are 3 different questions going on when we're trying to do vaccine selection. And one of them is really coming from the manufacturers. They want to make vaccines of high potency so they can be used in lots of different situations and they have broad coverage. The others are really questions for the consumer, which are, are there vaccines commercially available that match the circulating strains in my country, and are they actually available and affordable to me? Now, there's obviously a big question about whether or not anything satisfies all three of these criteria, but we're going to have to hope for the best on that and assume that there is an answer hiding in there that does satisfy this. Now, as far as the availability and affordability, we're obviously seeing this problem, particularly in East Africa at the moment, and work's going on to try to resolve that. But that's not really part of our remit. What we're interested in is how do you handle the fact that that there's this relationship between the potency of the vaccine and the antigenic match of the vaccine to your circulating strains, and what should we be doing to try to resolve this? And really, for me, and for us, I think the answer is that it's really only one question: that is the vaccine potent enough for the strains that we're interested in protecting against? And dividing it up into two different questions. The first of those questions, the potency against the homologous virus, is solvable, but the second of those questions turns out to be, whilst the computational approaches like Paolo's talked about and I've talked about in previous EuFMD sessions are useful up to a point, they don't tell us whether or not these vaccines are going to be useful. What we really want to know is if I have my cow here, is it going, and I vaccinate it, is it going to be a happy cow, or this may be a slight exaggeration, but my attempts at drawing a cow with FMDV failed, I'm afraid. And what we want is a vaccine that's obviously going to lead us to the happy cow over here on the left. And obviously in reality we have a lot of cows, and this is a wider scale problem, and so it's not just an issue which Alejandro was talking about earlier about sensitivity and specificity with individual animals. We need this to work at an aggregate level, which is a slightly different problem that we're trying to address. So I've talked about this before, and for me this comes back to essentially to Bernd presenting this back 10 years ago, but also to work with Paul Barnett in IAH, as was. And working on collecting large banks of antisera from experimentally challenged animals and testing different assays to see how well they worked. And so we started off with VNT and ELISA, and obviously the plan here is to extend that to new assays. And the problem we had, what you're seeing here is on the right, we have our predictions of protection for animals that were protected. So up here we have 100%. We're totally certain these animals are going to be protected, and down here, actually below the bottom of the graph, we're completely uncertain. And the problem is that so many of these vaccines are so good that actually the very low titers are still very often protective. And so these animals over here on the left, which actually turned out not to be protected, have the same titers as animals on the right that were, and so we incorrectly characterize them as probably okay. And that has knock-on consequences if we have a low potency vaccine or a lower potency vaccine, that we're going to incorrectly identify it as good enough for our purposes if we're just looking at a vaccine match. So what we did at the time to try to fix this was we basically added in all of the controls and said, okay, well these controls, they haven't actually been vaccinated, but we're going to just pretend that they were vaccinated with rubbish vaccines. And then we get a good differentiation between the ones that subsequently failed challenge and the ones that did. And we train with those data, and then when we go back to the animals that are actually vaccinated, we do get a better result, and we are better characterizing whether or not these animals are going to be protected or not. But we still have this underlying problem that we're overestimating how good the vaccines are a lot of the time, and it turns out that with unvaccinated controls, In the first case, we were estimating about 25% of them would have been protected. And in this case, we're still estimating about 6% of unvaccinated controls are going to be protected against FMD. And we know that that's not the case. So we know that there's a problem going on here. And happily, many years ago, Alejandra started trying to solve it for us, and her group down in Argentina. And so I'm just going to pick a slightly different graph out from the paper that Alejandra referred to earlier. And this is a ROC curve. For those of you who don't know what these look like, that red line there is what an absolutely rubbish diagnostic test would look like. And the green curve at the top is what a great one would look like. And what we can see is this dashed line is the IG1, IG2 isotype ELISAs are doing a pretty good job at distinguishing vaccinated from unvaccinated animals. So we talked, we've had a few meetings now, and we've talked about how this story should all fit together. And this is the story that we came out with at the last meeting, that essentially we want to know whether these animals are protected. And this is much simpler than obviously Alejandra's understanding of immunology. This is all that I could fit in my head. And to some extent, we're looking for what we think would definitely help will be high avidity neutralizing antibodies. And we have a bunch of assays down here that can identify neutralizing antibodies, and we have a bunch of assays over here that can identify high avidity antibodies. And amongst those are the avidity index, and I understand these isotypes, one of them has high avidity and one of them doesn't, but I may be wrong about that. Don't hold me to it. So then down under the neutralizing antibodies, as Alejandra said earlier, the VNTs, that's what they do. And the liquid phase are actually measuring all antibodies, which is slightly more indirect. And we found, and what I showed you a minute ago, was combining VNTs and liquid phase helps, even though they're both feeding into the same part of this equation. But adding something in from this side of the equation, we think would really help. And give us a much better idea of what's going on in terms of protection there. And so I'm not really going to talk very much about the results. You may have expected me to, but fundamentally the take-home story is that the IG1, IG2 isotype ELISAs work very well. These are sorted by quality. By predictive power, and the VNTs also work well, and then things get worse and worse, and you see that down here we have all of our R1 values, which are frankly terrible. But the problem here is just the numbers, and that's why I'm not going to talk about this in any great detail, because at the moment we have 88 animals, and those 88 animals all had the same vaccine. So that really isn't enough to completely convince us of pretty much anything. But you know, the work that Paul and I started 8 years ago with collaborators across the world managed to accumulate large numbers of challenged antisera. And so now when we look at these, and these are no longer sorted by number, we can't directly compare these numbers. They're just alphabetical. But we can see that now we have over 700 vaccinated and challenged animals that we've tested by ELISA. We have a similar number by VNT. We have more avidity than we do IG1, IG2. So we're building up stocks, and that's really what this part of the talk is about. Is saying that we need particularly heterologous challenges. We need those antisera so that we can put them together and test them and check that these results that we completely believe in, but these results are not a fluke, that we can reproduce these on a larger scale and get these assays out to more labs and have simpler ways of more reliably predicting whether or not this vaccine is going to work in your herds. So the samples have come from a wide variety of sources over the last 10 years. Ideally from you in the near future. Yes, and this is the group of us who've been working on this over the last few months. Thank you very much.